Let's go through quiz 3. Consider the following plot in the hypothesis space of the relationship between RSS and one of the parameters beta 1 for a linear regression model. So we have this plot here. This is of the error surface. And now the question asks is the slope at point A, at point C, and at point B. For this case, let's just go here. And we see that at point A, as beta 1 increases, RSS decreases. At point B, there's not much change in RSS. And at point C, as beta 1 increases, RSS increases. So because of that, we know that at point A, the slope must go down. So this is negative. At B, it is almost approximately 0. And at C, it is increasing. So it is positive.
So how do you know actually, like, where do you see that, like it's increasing or decreasing? How do you actually know at like point A, it is decreasing?
At point A. So it's like this, right?
Yeah.
The slope is actually like this. So where do you see it? So you see that as beta 1 increases, we know that for a small change in beta 1, we know that RSS goes down, right? We look at 0.5 and at some point next to 0.5, we see that RSS has come down, right?
Yeah, I mean, that intuition is not very clear to me actually. So how do you?
No, for a small change in beta 1, let's just take a small change and the curve is like this, right? So for a small change in beta 1, we see that there's a downwards change in RSS, right? So it's like this. So we get a negative slope because there is the change is negative.
Derivative is delta y by delta x.
Right? Yeah.
It's essentially that's all it is. For small positive delta x, you are getting negative delta y, so that's why it's negative.
Yeah.
And then you're rising up on the other side, it's a positive. And since this has the contour is such that you always have a bowl at the center, right? The RSS can only go down, right? It can, that's the reason, right? It cannot go, it can go up, but you know that it's going to have this, bowl shape.
Yeah, parabola shape, yes.
Parabola shape.
For the intuition, at point B is the local minima.
Correct,
Yeah.
local minima, correct.
Yeah, so that's why, you're going up and down. So our main reference is point B.
Sorry, yeah.
Especially at point B, we know that there is not much change. There's no change in RSS as we move along beta 1 for a very small step. And because of that, slope is 0.
So for A, we are moving in the direction of the gradient or opposite to the direction of the gradient?
Opposite to the direction of the gradient.
So where is it's pointing down, right? So that is the direction of the gradient, or that's the direction of the error surface?
So you always
gradient is different.
Good.
Gradient will point in the direction of greatest increase, right?
Yeah, so for point A, where is the greatest increase?
So we don't look at this curve, but rather we look, so gradient is something where we look, it's mapped on the parameter surface, right? Beta 1, beta naught, and it is a vector on this surface, and it is not actually marked on on this curve or anything. So in that case, we have the bowl like this, okay? And then we talk about the gradient, and gradient will have two, it's basically delta RSS by delta beta naught and then so forth, right? So it's like something like this. This is the gradient, right? So, and this gradient, it's marked only on this parameter surface. And if we look at point A and we want to know the gradient, it will always point in the direction of the greatest increase. So, and that would be away. Away from.
I think the other way you can look at it is, Anil.
Yeah.
Say, can you bring that graph back? Yeah. Just look at point A, okay? Assume that there is no minima, nothing. Okay,
Mhm.
you are just seeing point A.
Yeah.
Just move a little bit, right?
Yeah.
Move in any direction, right? Any direction you move over there, delta beta 1 if you move, you find what is the difference of the RSS, right? So what happens is, if you move in the positive direction, the RSS reduces, so it is negative. So the movement is always opposite of that to the derivative, which will get you to the minimum. So in this case, since the derivative is negative and you go minus of that, you have to keep increasing beta. On the other side, if you were to come on C side, right, and you're starting your journey from there, then if you come down, the derivative is basically positive. So you know that you're going in the opposite direction, minus. So that's why you have to reduce. So that's essentially the, what do you call, the intuition. If you look at it at the big curve, you don't know. But what you have to do is kind of just concentrate yourself at point A. Think there's nothing else around, right? You're just on a hill and you want to go to the ocean. How do you go to the ocean, right? Are you going to go with your feet that gets harder for you to go up, or are you going to go down where your knees are going to be easier, right? Correct. If you're on a hill and you want to go to the ocean, wouldn't you go, you know that the ocean is down, right? That's the way I usually, that's why they're called as contour maps or hill maps or things like that. Okay, I'll let you
Okay.
go ahead. Right. I don't know if I explained or confused. So,
Okay, sorry, Sachin, can you explain it at point C then?
huh?
Whatever you told just now, that
Yeah.
intuition, can you come from point C?
Yeah, so any point you look over there, right? Just assume that your universe is just around point C, correct? You take a little bit of a displacement, any direction, right? Whether it be the displacement goes delta beta 1, right? And if you take it in the positive direction, what happens is the slope is going up, which means you have to go opposite. The direction that you have to go to the minima is always opposite to the slope of the derivative. Right.
Okay.
So there, that's why it tells you that, hey, you don't go in that direction. You have to go down. That's why I gave the example of ocean, right? If you are on a hill and you have to go to ocean, what does your legs tell you? If you keep climbing up, you know that you're going away, right?
Yeah.
It hurts, right? But otherwise, if you're going down, then you know that you're in the right direction. That's the way you should think. Like there's a very small person over there at that. Sometimes the books show that small person sitting over there in that the universe. He cannot see anything beyond this whole thing. Yeah, that's all he sees. Little bit. That's how you should think.
And he'd rather slide down like this.
Yeah.
That's another way to think of it.
Thank you.
So for this question, we're asked to find the type of error for each of these. And in this case, yeah, so I have a map here. So here we see that for this particular graph, all the points are crowded around the center. So if we draw the distribution, it will look something like this. So look something, it will look something like this. So in that case, we have comparing the other 4 maps, we see that this has a lower spread, and because of that, it has lower variance. And also bias is less because the 0,0 is the actual point. So there's not much deviation of the mean from the actual mean, and because of that, there is low bias error. And here we have a large spread, and also, but the mean is the mean of the of the data points match the mean of the actual point. So because of that, we see that this has high variance but low bias. Here the mean is shifted, so there is high bias and high variance. Here the mean is shifted, but comparatively the spread is low. Because of that, there is high bias but low variance.
Oh, are you using a mouse or something like, because we couldn't see the mouse? Like,
this is the same issue.
oh, okay.
This is OneNote. So I was talking about this first, and then second,
okay,
third, and fourth. Yeah. because I can see the mouse and I keep
I
forgetting.
know, I know mouse is in black color and you're going there on the black color. Maybe you want to change, if you change your mouse color to something different, I think it might
Okay.
work.
Yeah, I won't be going there anymore. So it's fine.
Oh, okay.
Now, consider a linear regression model y equals beta x. In the equation above, we subsume beta naught as part of the beta vector and x vector as the augmented vector. While the training of the model is in progress, let the total error be given by E beta. The equation for a gradient descent step of learning the next values of beta parameters is given by. So we know that beta next is equal to, we go just like Sachin said, we go in the direction opposite to the gradient, right? So we need to go in the direction opposite, and then we have the the size of the step depends on the learning rate here. So the answer would be this. Let's just check if I'm right. Yeah. So it's beta minus the current step minus a small step in the negative of in the direction opposite to the gradient.
So the other intuition that I always use with the alpha is essentially, do you have an adult versus a child, right? The adult will have long steps and reach faster versus the kid has smaller steps, right? So that's essentially that delta thing, that kind of. So otherwise, it's hard to figure out where that alpha goes in most of the time. So
Okay. So consider that we are trying to fit a polynomial regression model of degree 20 to a data set D. For this data set, we draw four different samples, A, B, C, D, of increasing sample sizes. When we fit the polynomial regression to the four samples, we end up with four different models, model A, model B, model C, and model D, that capture the relationship between the feature X and response Y. Select all the statements that are true based on the plots given below. Okay. So now they're asking about the variance errors. So in effect, we're only asking what happens in the test case, like in the real world scenario, when we apply these models, what would be the variance errors? When we look at these four samples, we can see that there are more samples here, and therefore there must be more error, but that is not the question. We are asked, when we apply this to the real world with the same data set with different samples, what happens? So in that case, we know that this model seems to be quite off, right? It has a lot of oscillations, and because of that, when we apply it to a data set like this, as in sample D, it will have a lot of error, and that would be a lot of variance errors. And so we know that model A has the most variance errors. Model C has the most variance errors, compared to A, C has comparatively lesser variance errors. It is slightly more regularized since we have trained it with more data. And model A has most bias errors. That is not true, because this is not underfitted, but rather overfitted, and we will see a lot of variance errors. Okay. While training a machine learning model on a data set D of observations xi, yi, a point beta in the hypothesis or parameter space corresponds to yes, a specific observation or datum that is on the data space. Error of the model, it's the curve. It's the hyperboloid surface, but that is on top of the hypothesis space. A specific instance of a hypothesis or model. So this is the right answer. Okay. Yeah. During the training of a model, what happens when the learning rate alpha is too high in the gradient descent process? So will heat up the machine and lead to hardware failure? No. Possibly the successive values of beta oscillate around the minima, unable to converge any further to a lower model error value. So this is true, because if we have, say, a higher So we do have a large training rate. So we'll sort of jump like this, and then, okay, now this one is right wrong. So if I jump like this, I'll come here and then I'll go back here again, and I'll keep jumping around the, the actual minima, and never, it will be, I wouldn't be able to converge if I don't reduce the learning rate. Then possibly the true minima may be skipped, thus producing, sorry, what happened? Yeah, possibly the true minima may be skipped, thus producing suboptimal parameters. That is also true.
I can't see that.
Screen kind of goes back and forth.
Yeah, I don't know why.
Yeah, now it's fine.
Okay. Possibly the true minima may be skipped, thus producing suboptimal parameters. This is also true, as we saw just now. Then great idea, since it will lead to quick convergence always and save computational time and resources. This is not true. So it might not lead to it might be quick, but it will not lead to a good minima. So same question. The correct order of the models with respect to their variance errors. So it's a similar question, but now we are ordering all the 4 models. So as we saw, A has the most variance errors, B has comparatively less, C has a little bit lesser than that, and then D has the least, because it is more regularized and it fits the model more truly, to the data. So in this case, we know that D has the least, and then comes C, and then B, and then A. Okay, so this question, I guess a lot of people got it wrong. It's there in the question, the answer is there in the question. So consider that we are trying to fit a polynomial regression model of degree 20. So here in the question, we've given out that all these models are of the same degree, right? They're of the same polynomial degree and same complexity to a data set D. From this data set, we draw 4 samples, and so it's the same question. Select all statements that are true based on the plots given below. Okay, so model A is surely more complex than model D. So a lot of people had selected this answer because it looks like it, though. It looks like model A is more complex. But the fact is that this model D has been regularized because there has been more data. And because of that, it's almost like a straight line. In spite of the fact that this is also a model of complexity 20. So model D is the most effective in capturing the relationship between X and Y compared to other models. That is true. Model A is surely more complex than model D. That is not true. All the models have the same complexity. That is true. And this is also not true. So let's fill in the right responses. Yeah.
Oh, so only one is correct?
2 are correct.
Oh, which one?
Wait, sorry. Model D is the most effective in capturing. That is true. All the models have the same complexity. That is also true, because that is right here in the question, that all of them have the same complexity. It just looks like they don't have the same complexity because of we've taken different sample sizes, and because of that, it's been regularized. And also it's given that all of them have been drawn from the same data set.
Okay.
I think the key thing to take there is the fact that regularization kicked in
Yes.
D. And that's why,
Exactly.
yeah, I got it wrong. I kind of didn't discern that.
Yeah, that's the point of discussion, to confuse you. So yeah, and the last one, okay. So now this is the same question, and what we are asked is, from the plots below, one may reasonably infer, okay, we're asked to infer what do we need to do to the complexity. That the most effective yet simple model is probably a polynomial degree of 10. That's quite random. That's not true. Perhaps a linear regression model of, yes, polynomial of degree 1 would be quite effective. That is true, because as we see, when there is more data, it looks almost linear. So why would we need a higher complexity? So that would be the right answer. And this one would be much greater than 20. That is also not true. That would be even worse. The most effective yet simple model is degree 19. Yeah, and that's just, yeah, not true. Through the gradient descent process, we are guaranteed to find the optimal parameters for any machine learning model, however complex. This is not true, because we will not, if there is a global minima much lower, I mean, if we might end up in a local minima and not in the global minima. So this is false. Yeah.
I'll add one thing to that. It is true only when the loss surface is convex. Many machine learning problems, in fact, deep neural networks, don't have convex loss surfaces. Linear models have that quality, and generalized linear models have that quality. That's why you can, with gradient descent, achieve the minima, but in other places, you don't know whether it's absolute minima.
Yeah, so that is like, so if the local minima is equal to the global minima, then, right?
Yeah, see, this is a whole body of research. For many years, for example, in the 90s, we used to worry a lot about simulated annealing, that if you get trapped in a local minima, how do you jump out of it? And you brought in considerations from statistical mechanics and thermodynamics that, the process of annealing metal.
Yeah.
Yeah, so you would you take it to a lower and lower energy state, because every time you cool it, the crystallization that forms, there are defects. So it's a higher energy state. So you anneal it. So people thought that we would do a lot of research on annealing and go there. Today, the thinking is different. We do have simulated annealing, but it's not emphasized so much. The general thinking is that there is a deep relationship between the minimas that we are only beginning to get an inkling of. One of the findings that people have is that, and we did that in the loss surface paper we covered in ML400, but not for you. What we saw is that they may be interconnected. They may not be the same minima or the same energy level, but they may be interconnected through ravines and so forth. So it was a fascinating set of findings that people are coming out with. It's still a very active area of research at this moment. So, and how much initialization parameters the random initialization plays, we are finding it's pretty serious. For example, the lottery hypothesis that based on your random initializations, more or less are minimized. I mean, a subnetwork is preferred that goes to one minima. So we won't go there at this moment, but generally to remember that whenever you have a convex model, you have that. That is why in machine learning, when you look at optimization, there is a whole field called optimization theory. In optimization theory, linear optimizers are, of course, a given. Then convex optimization is a whole topic, and we try very hard to make our problems convex. The deep neural network people sort of came and they found that it's not so absolutely necessary. They call this search for convex loss functions to be, jokingly, they used to call it convexivitis or something like that. So anyway, we don't know. All we know is that gradient descent is guaranteed to succeed only if you have a convex loss function.
So Asif, that annealing process, was that like related to the cosine annealing, or that is just one type of annealing?
Lot of it. Annealing is a broad topic. It's borrows from physics, statistical mechanics, the annealing of material. So We can talk at length about it. I mean, today is not, because there are people here who are doing ML, this thing, data science course for the first time. So it's probably not appropriate to go in that depth, but maybe for another day.
Okay.
Okay. The first question. The model that is overly simpler than the ground truth tends to have high what kind of errors? The options are bias, irreducible, and variance. The answer is bias errors. And the model that is overly more complex than the ground truth tends to have more variance errors. This is overfitting, this is underfitting. The first one is underfitting. Okay, the second question. Okay. Select all statements that are true based on given residual analysis for the polynomial regression hypothesis H of a data set D with predictor variable X and response variable Y. Okay, so let's see, these are the three graphs. Okay. Yeah, we observe larger training residual errors compared to the test residual errors. The first statement is not actually true. We see it is almost equal, right? So we don't have a big difference here. So we observe a larger test residual errors compared to the training residual errors. No. The training residual errors and the test residual errors are similarly distributed. Yes, true. You can see the distribution here, even on the distribution of the residuals, right? You can see the overlap is almost same. There is little difference, that's it. The hypothesis can be very significantly improved by training the model with much more data, not really. We can see the distribution is good, and we can even see this model is pretty well fit. Since there are no pronounced patterns in the residual plot and there is approximate homoscedasticity, the current model is probably an effective one, and other models will not be significantly better. The second graph shows us homoscedasticity and there is no significant pattern. That's why that statement is true. The model can clearly be improved by reducing its complexity, that is, considering a polynomial of a lower degree. No, this is good. A model can be improved by increasing complexity. This will get it overfitting, so we don't want that. The model has overfitted the training data. No. The model has clearly underfitted the training data. No. This is a good model, pretty good model. Okay. Next question.
Back, and can you tell me why the other one is not? There's a one we said that you can reduce the improved by reducing its complexity, that is considering of a lower degree. So how do you know that something lower cannot be good? Or I don't know if is that obvious?
It's not obvious, right? But here you can see the model is pretty good, but if we do reduce it,
see, we see that this one looks like a polynomial of degree 3.
yeah.
Okay, next if we reduce it to 2, it will be a parabola, and obviously that will be a bad fit. And then further, if we reduce it, it will be linear, so it will be a straight line, and even a straight line doesn't seem to fit it properly, right? If you fit a straight line,
you are assuming that this is basically what do you call it? Quadratic, right? 3 degree 3, right?
You mean a polynomial?
It's a polynomial. If you put a straight line, if you can see there is extension, like there's data is under, if you see x minus 10 and plus 10, do you think a straight line would fit this model? There is, I don't, there is, concentration of data in a curve, right?
No, so that was not my question. Was, say, suppose this was degree 10, right? And there were, like, from the earlier thing that you had, remember you had those small and all. So rather than 10, if you had, say, made it 8, would that have fitted better? That was my more question.
I think you'd start
Okay.
seeing patterns in the residuals.
Right.
Yeah.
So, I
We'll
mean,
have to try and see. Yeah.
yeah. So I don't know, but what I was thinking that.
Okay. Yeah, but since it's homoscedasticity and the distribution is almost Gaussian, right? Normal. We don't say this is the best model, it is a good model, right?
It's just that there's a lot of variance, irreducible error in this model. And that is the takeaway. And there, even if you try to fit a better model, you still, like, even if you increase it by 4, you have a lot of data, so it will definitely be regularized. But the point is, since the data points are very much scattered, there's a lot of irreducible error, and there's not much more you can do. That is the takeaway.
Yeah, one more question here. On what basis are we saying, like, I mean, this residual plot has no pattern, right? I mean, we see a straight line in the center.
No pattern in the sense there is no obvious, say, there's no bias errors, right? There we don't see a concentration of points at one side, but all this is more related to how this is probably because of how the training and test are distributed, and probably because of the curve here, but it's not related to say a bias errors, right? So that's what we mean by we don't see any pattern.
Okay.
No, when you see the pattern, it is the variance, right? So it is not the variance. Like, you don't see the variance in the middle graph.
Yeah.
Like the homoscedasticity and heteroscedasticity, that's the difference, right? Because you see the variance increasing. So that is what you see, that's what is the pattern, what you see. So in this, you don't see the pattern. So it's not biased, like it is, I think, only the variance part here. You don't see the variance in the residual plot.
What I meant was if we fit like a model with polynomial degree 2, we'll see obvious pattern, right? We'll see a cluster of points on either side of this line at this, the line at 0. So that I meant by pattern. But yeah, there are two kinds of pattern. One is related to variance and one is related to bias. So with variance, we'll see heteroscedasticity, and with bias, we'll see an obvious underfitting, and we'll see points significantly to one side of the
one quadrant
line. Yeah.
If you still have doubt if Asif sir is there, we can ask him to explain.
He's there.
Yeah, so it's clear for it. Sir?
I think he's away. Yeah, we'll move.
Oh, hi. Did I hear somebody calling?
Yes, sir. Can you? We have a few questions on the second graph.
This graph, huh?
Question 2 that.
Why do we see this line over here?
Line there. Is there a pattern?
Predicted value. See,
Yeah,
let me look at this question. Select all statements that are true based on the given
Vertical
analysis of that and a data set with the predicted. See, this is the nature of the data. If you look at the way the data is there along the left graph, just focus on the left graph. And just imagine that all the points here collapsing against the wall along the y-axis here collapsing. In your mind, imagine the bell curve that will take shape. Where will it be peaked? Where do you see most of the points here hitting? Most of the points that you see
within the 2 sigma distance, right?
Yeah, they are basically around the origin, right? Around 0, but yeah, spread around it. So now you look at this predicted value. Now look at the center graph, and imagine that forget the residual part. The y-axis here in the center is the residual. but ignore the residual part. Just imagine that all of these green point, all of these points here are squashing down, you're projecting down to a bell curve on the x-axis. The bell curve that will develop along the x-axis, would it be very similar to the bell curve that is already there, that is along the wall of the y-axis in the left graph in your mind? Right? So reason this thing through, guys, and you'll see that it will be. And so you have a concentration of points here around predicted value 0, because in the real data itself, there is a huge concentration of points along that place. Okay. Right. That is what it is. So remember, when you look for patterns, you look at you keep your eye on the residuals, not whether as you move from left to right, the number of points are increasing or decreasing. You look at the band, how much variance you see. So in the center graph, look at the variance. In the middle graph, with the mouse, Kyle, could you please show? Yeah, look at the variance, the width of the errors, width of the residuals along any x value. Any predicted value. Do you see them changing much? Sort of, very mild, probably not, right? These are pretty much, it's a uniform with respect to that. That is what you look for. You don't look for the concentration of data at certain points. You look for the band of residuals. You focus only on the residuals there.
So we are focusing on the variance and not the bias, right? Or like both of them?
See, a bias will show up immediately as a huge pattern, but when you, the variance errors, here when you look at this picture, look at the band of errors. If the band is, which is measured by variance, if that doesn't change, then you seem to be in a good place. So neither of the two should be present. When you build a model, if you see a clear pattern or you see the heteroscedasticity of the residuals, both of those are bad. And if you notice in the lab, I tend to make a point about both, isn't it? So from that perspective, here there is no pattern except the inherent centering of the data around the origin, predicted values around the origin. That comes from the fact that data comes to you, original data comes to you like that. Now, if you look at the plot on the left, and in your mind's eye, projected down to the y-axis as a marginal distribution, you'll see that it is like that. So that is okay. So now, what was the question? Was that the question?
That was the question. Yeah.
All right.
Yeah. So you mean to say the data concentration is 0 and 0. So that's why there is a lot of points. That's it, right? In the predicted value.
Yeah, and in fact, this is one of the key things that as you get trained in these things, you know what to look at and what to ignore. That is one thing to ignore, because the interpretation, not ignore, but you look at the left and you know that is the nature of the data. So you say that is fine. All right.
Yes.
Yeah.
Thanks, Asit.
Yeah.
Thank you, sir.
If you have any questions for me, would you like to ask right now? Because I was going to hit the road to go back home.
Okay, just one more. This one.
Okay.
Yeah.
Data set D of n instances, depicting the left plot below. A polynomial regression model is fitted to this data. The error of the model is measured as the mean. Okay, that is it. What is the optimal value of n? See, the optimal value of n is, first of all, the lowest test error, and amongst all the points that exhibit the same low test error, which of them is the simplest? So when you look at this, what would you say? At what value do we achieve minima of the test error, and it is still a simple model?
4.
Yes.
Yes, that's right. It's just that when I plotted this with the polynomial of degree 3, but somehow the error for degree 3 is pretty high, and I'm not sure why that's happening.
There must be a bug in here. See, if you believe the plot on the right, then the answer is 4. If you look in the curve on the right, there are points in the data. two bends in the data,
Yeah.
but because you made it about mean squared error, therefore the only plot that matters is the one on the right. But if the only plot,
Okay.
if it was about here is this data on the left, what would be the optimal end to model with, to start with? What would be the simplest end to start with? Then the simplest end to start would be n is equal to 3.
Yes.
Okay.
That, so in from that perspective, but go and check. There is a bug in the way you.
There's a bug, right? I mean, like the n is better than 2 is better than 3. How can that be?
Sometimes it happens.
Yeah.
It does happen during training because training starts with random initialization points. But generally, linear models, and polynomial is a linear model, it tends not to happen. Almost surely something is screwed up, right? So run it again. And
one
Yeah,
thing which I am noticing
Kyle,
is,
you can show the third question. So where he's coming from, right?
one moment, somebody had a question on this
Yeah.
question.
Okay.
so what I am noticing is that the training data have more on the lower side
Yes.
compared to test data. So test data is missing at that end.
That is quite possible and very, very
Yes.
good point. See, I didn't notice that, but assuming that that is true, let me, I'll have to bring my reading glasses. But assuming that that is true, that explains, see, the assumption in a test and train data is IID, independent and identically distributed sample points, right?
Yes.
Training data set and the test data set, they cannot be different distributions. If they are different distributions, then you will start seeing odd things like this. So,
but it looks like it is like from the same distribution, right?
it does look, actually, to me, it doesn't look very different. But
yeah,
my own guess is there's something odd about it. Look at the code and run it again carefully. You'll find some little glitch there. Yeah. For such a simple polynomial model of degree 3, learning rate convergence should have been very, very, it is steep, like going down to 2, it is already coming down, but it shouldn't have stopped at 2. At 2, the test error is too low. It shouldn't be this low. Something happened. If I have to guess, most likely you mixed up your 2s and 3s. If you look at the green line and you look at the on the right hand plot, the green, and you interchange the value for 2 and the plot will then make perfect sense.
No, I actually took it as a range. So I plotted it for range from 0 to 10. So it's in order only.
No, I'm
but
not.
Yeah, I'll check it. Yeah.
I'm saying that if your data point, the same graph, if it was reversed, the value the error achieves at 2 is actually the error that it would have achieved at n is equal to 3. And the error value that it achieves at 3 is the value that it would be at 2. Then the function, then the error test error would be also more or less monotonically decreasing at that moment, right? It would decrease like this. So anyway, try it out, see what happens. Maybe you can show me the code after this. I'm going to drive home. Any other question you want my input on?
No, that was the only thing. Yeah.
That's the only one, sir.
Yeah. All right. Yeah. Bye.
Thanks. Sir. Yeah.
Okay, so the third question. Select all options that are true based on the plot given below. Possibly the optimal value for n is 6. Okay, here n is the model complexity, so the number of bends. 6 we don't see, right, those many. Possibly the optimal value for n is 5. We don't see those many bends either. More data is required for analysis. Possibly the optimal value for n is 10, so which is not true. So we need more data for analysis. That's what it says. Okay.
And there's just too
sure
less
a lot
data.
of us selected 6.
Yeah. Okay. Next question.
Okay. Yeah.
Yeah.
This one we just went through it.
Yeah. Fifth one. Okay. Consider a univariate data set D of n instances depicted in the left plot. the polynomial regression model is fitted to this data. The error of the model is measured as mean of squared residuals, that's MSE. What is the optimal value of n? So we are trying to find the complexity based on the MSE here. So here, possibly the optimal value for n is 8. If you can see at 8, the test error is increasing and the training error than the training error. So this is not good. Possibly the optimal value for n is 4. At 4, at this point, you can see it's, the test and the training error is similar, but later, the test error is increasing. So at 0.4 is the complexity we have to consider. So possibly the optimal value for n is 4. That's the correct answer. Okay, question 6. Select all statements that are true based on the scenario described here of a polynomial model H of a data set D with predictor variable X and response variable Y. The left plot shows the predictions overlaid on the scatter plot of the data. The middle plot shows the residual errors. With respect to the predicted values Y hat, the rightmost plot shows the histogram of the residual errors. Let's see the options. Due to underfitting the training data, the model exhibits larger training residual errors compared to the test residual errors. It's not underfit, right? Yeah, so it is a complex model that's being fit on the data. Due to overfitting the training data, the model exhibits larger test residual errors compared to the training residual errors. This is true. We can see due to the test residuals are large than the residuals of the training data. It's increasing, so that's why it's true. The model can probably improve by training with more data. That is always an option, so that is true. The model cannot be improved by increasing or decreasing its complexity. We need to decrease the complexity, so it's overfitting here in this scenario, so this is false. The model can clearly be improved by reducing its complexity, that is considering a polynomial of a lower degree, that is true. The model can clearly be improved by increasing its complexity, that is false. Yeah. So here there's high variance error, so we have to decrease the complexity. The next question. Okay. The 3 components of prediction error are, so what the definition of error? So it's the sum of bias error, variance error, and irreducible error. The 3 components are bias, irreducible, and variance. Okay. The next question. Okay. Select all statements that are true based on the given residue analysis for the polynomial regression hypothesis H of a dataset D with predictor variable X and response variable Y. So blue line is the model, X and Y, and this is the residual analysis. So let's read the options. The model has underfit the training data. This is true. The data is more complex than our model. The model has overfit the training data. That is false. Since there are no pronounced patterns in the residuals plot, there is approximate homoscedasticity. The current model is probably an effective one and other models will not be significantly better. This is false, right? We can see a clear pattern in this data. The model can clearly be improved by reducing its complexity, that is considering a polynomial of a lower degree. This model is already too simple. So we need to increase the complexity. So the next option is right. Okay. In the context of a linear regression model predictions, the presence of heteroscedasticity in the residuals plot may be indicative of the need for a different relationship between the predictors and the response that is being suggested by the model. This is true, like how we see in the previous question, right? There is a pattern. So heteroscedasticity will give us a pattern. So we need to build a better model. The next question. Consider data set D where the histogram of the target variable Y exhibits a pronounced right skew. In the context of a linear regression, that is indicative that one must specifically avoid performing a power transformation of the target variable, as that will degrade the predictive power of the model learned from this data set. If you remember the diamond data set, the target variable price was right skewed. To to do the to correct this, we use power transforms, and it's in inbuilt log transform. So under the hood, it is a log transformation. So this helps in handling this right skew data. So we have to do, so the answer is false. I think that's it in this quiz.
Yeah, that's it.
Yeah, that's it.
It's over.